I will present our work, AudioViewer Learning to Visualize Sounds. Our goal is to enable sound perception for the deaf and hard of hearing people. We want to achieve the goal by translating sounds to images, making people perceive the sound signals by watching the corresponding images. Here are the most related audio-to-image works. Among these methods, audio-to-scene methods focus on high-level translation between sound signals and scenes. It's unable for people to learn sounds from the generated images. Audio-to-gesture methods usually focus on music. The goal is to explore the relationship between the gesture of playing instruments and the music sounds. Both audio-to-text and audio-to-lip motion methods focus on human speech. The difference is that audio-to-text methods can only translate human speech at the word level, while audio-to-lip motion can translate phoneme-level speech. But the problem is that it tends to be ambiguous. For example, ball and door share the same lip motion. So in our paper, we propose a general phoneme-level audio-to-visual mapping through which people can learn the sound from the corresponding image while overcoming the ambiguous problem introduced by audio-to-lip motion. First, it's natural to maintain the frequency of features during the translation. The commonly used sounds should be mapped to the commonly appeared images, and the uncommon sounds should be mapped to the uncommon images. So our method is unsupervised based on unpaired examples. Then, because humans are good at recognizing visual patterns such as faces, we use facial images as a representation for sound signals. Another observation is that quick and unnatural changes lead to disruption and tiredness, so we introduce a smoothness constraint. Therefore, we learn an audio-to-face mapping from unpaired examples with smoothness constraint. Based on the motivation, we design our architecture like this. We take the male spectrum of sounds as the input of an audio encoder to get an audio latent code, and then we map the audio latent code to the visual latent space through a translation modular. Finally, we decode the visual latent code to image domain. During the training stage, we train one audio VE and one visual VE. We first train the audio VE using VE objective and a smoothness constraint so that the latent codes can echo the sound changes with time. We also learn the disentanglement of sound style and content, so we can choose to translate all sound signals or just only the content signals or style signals of sound. We then train the visual VE using the VE objective. Finally, we connect the audio encoder and visual decoder with a translation modular, which is trained by a cycle consistency loss and smoothness constraints. Here are our human speech visualization results compared with Make It Talk, a lip motion translation method.
She had your dark suit and greasy wash water all year.
She had your dark suit and greasy wash water all year. Her wardrobe consists of only skirts and blouses.
Here are our environment sounds visualization results. We further validate the learnability with the study. Here is the accuracy learning curve. It shows that a set of words can be successfully learned with our novel representation. Please check our paper for more details and results. Thanks.